Hello, my name is Dan Daly. You weren't supposed to be seeing me again. It's because I was filling in for Naru. So building on the previous presentations from before, starting with Joe and our discussions around OPI, it's demo time. So a lot of this presentation is a YouTube video, so like my kids would love this, but it's Artyom and Philip would love to be here today, but they couldn't travel across the Atlantic. But they've created a demo for you that is going to walk through piece by piece the different APIs that we've developed in OPI just for storage. So it's a cool demo. I'm going to try to give you some background on what is it that they're exercising and how they're using it. And I'm also going to show another demo with the Marvell part as well. So let's get into it. So if anyone wasn't in the first presentation, we talked about OPI, and if I'm going to tell you two things about OPI that we're trying to do. One is we're trying to make it easier to deploy these devices with our OPI provisioning work group. And we're trying to make it easier to run and maintain these devices with the OPI APIs that we're defining. And within those OPI APIs is what we call the storage recipe. And when we're talking about storage, we're talking about virtual block storage. That scope may grow over time, but just all these presentations this morning are around how do I give an end customer, whether that customer is in the cloud or on-prem or in their own environment, how do I give that end customer a virtual block of storage, a virtual disk, a virtual controller with lots of disks underneath it that can hold their data for them in a hardware isolated way and in a resilient migratable way. And we haven't seen this picture yet, but it's exactly the same picture that we've been seeing in the other presentations, where I have an initiator and a target. The initiator is converting these storage operations into packets, and then those packets are going to some number of targets. And on their way through, the data may be encrypted, it may be compressed, it may have certain checks to make sure that the validity checks to make sure nothing was corrupted. And then once it lands in the targets, most targets today, and this goes beyond the NVMe spec, will then apply certain resiliency approaches, whether they're replicating lots of copies in different places, doing erasure coding or something like that, to ensure that once that data is stored, it's never lost. Even after the target's unplugged or something horrible happens, your data center breaks, never want to lose a bit. And so if you zoom in on that initiator side, we have from cloud this abstraction where within a host, within a virtual machine, or within a container, I want to offer these virtual devices to compute. So if I have cloud compute, I'm going to say, all right, well, I need this number of cores, I need this amount of memory, and I need 3 network ports to talk to my 3 different networks. I need 5 disks, because that's where how my virtual data is stored. And I'd also like a virtual GPU, please. And so we apply this abstraction, and we use it everywhere. We use it in VMs, we use it in bare metal hosting, and we use it in containers with Kubernetes. And so the value of this block storage initiator with a DPU or IPU is that there is no footprint on the server in any way. We make 0 assumptions about what is on the server other than it supports PCI. And so this saves a lot of cores. It's a clear question. How many cores are used in order to support these block devices? The answer is 0 on the server. And that also makes deployment much simpler, because now I don't need to make any assumptions about, oh, well, in order for me to provide my service, the server needs to have this OS with these patches and this application running and this script running. None of that's required. So it completely decouples the host server from the infrastructure, making things a lot easier to deploy. And so you can imagine, if you're a cloud service provider, this is exactly what you want. You have hundreds of thousands of these servers, and they're a mess, and you don't know what's running on them. And so you need this DPU, IPU, just to have a place to stand for your infrastructure, software, hardware, whatever. And then once you provide that separation, you can now provide to your end customer these resilient disks that move and migrate with the application that's needing them. So I can start my job, load up half my data, and start my training my AI, and then maybe my model goes and I reinstantiate that. I just take that disk and I reattach it to the new instance that I'm running. And so there's no need for a cloud service provider or the person providing me with my infrastructure to say, oh, I moved you from this location to that location. Let me go like unplug your disk and move it over here. All of that is automated within the virtualization layer. And it seems super simple, but it's super powerful, because now I can have that certainty that my data is always accessible to me. And I can be certain that in that process, none of my bits were messed up. And also I can, as an infrastructure provider, give certain guarantees, because I'm going to be hardware backing those devices, whether they're ports or disks or GPU instances, with hardware QoS. So hardware isolation, hardware tenant isolation, and hardware rate limits to make sure that no one, maybe I only bought a 10 gigabit port, but I tried to use 100 gigabit. The DPU and the IPU will enforce that you only get what you pay for. And then an important part of this virtualization layer is that I use all standard drivers. Because I don't know what's on that host, I don't know the software, I don't even know the OS, I need to have a driver for the network, the disk, and the GPU that is going to be common enough in that host so that enough customers can use it. Otherwise, you have to have your customer, after they go and they deploy themselves on the cloud or deploy themselves in your cluster, they have to go and, all right, well, where's the driver for the disk? It's like, the old Windows machines, and it's a mess. And so we use standard drivers in here because we know that they're going to be there in the operating system for the end consumer to use. So I think that the question came up here is like, are you guys creating a standard so that there can be a standard way to go and set all that goodness up that I just mentioned? And so instead of creating a standard, what we've done is we said, all right, we're going to define a common set of gRPCs for storage. None of it's surprising. Create disk, set the size, set up the multipath, all these things. And then we have different vendors providing different, we call them bridges, that bridge from that OPI API at the top to each of their different implementations at the bottom. And some vendors like Intel and Marvell have different devices, and so they can provide the multi-device abstraction within their bridge as well. And so you can go onto the GitHub today and you can see Marvell's bridge, NVIDIA's bridge, Intel, there's one from AMD, there's a couple others that are on there. you can go straight to the GitHub and it's all there for you to see. And we expect this model to be useful in other domains beyond storage. But for today, we're going to demonstrate a set of these APIs that we've defined and have implemented on. In this case, it's a Intel E2000 IPU, but we also have this same bridge running on our FPGA-based family of IPUs. So let's go. So I don't know if you can see this, but this is a demo of the Marvell bridge running here. So we are creating devices here. It's so hilariously small. I can pretty much just make up what it's doing. You can't see it. But if you look at each block, on the infrastructure side, we're going to set up the disks. The disks are going to show up on the host, and then the host can use those disks as storage. The host has no idea that this is a Marvell part or an Intel part or whatever. It could be pure software, actually. All works the same. But the key piece here is that when you are using a DPU or IPU, this demo here is using all of the APIs that are inside that OPI project, OPI Marvell bridge. And it's hilariously small, actually. I think that's funny. To go into more detail on what are these OPI APIs for storage, we have a little map of the world, also maybe slightly more readable than the last slide, but it's everything that you would expect in a storage API. I've got devices, I've got disks, we support both VirtIO and NVMe, and we break down the APIs into three important subsections. The front end is everything that's facing the host. So remember that inside of OPI today, we're really focused on the initiator side. And so on the initiator side, it's important for us to be able to do all of that memory management functionality where I am creating a disk and inserting it into the host, sometimes dynamically. A new instance will arrive on the host, and you say, oh, I need 5 disks. So those 5 disks will pop into the PCIe for that instance based on the configuration that was done on the infrastructure side through these APIs. So all the things that you would expect, we'll show some of them in the demo on the front end. The middle end are some of these services that were talked about earlier in terms of once I have that read, write, flush, whatever, on the IPU, DPU course, then what am I going to do to that data? Am I going to encrypt it? Am I going to hold it a little bit so that other higher priority traffic can go across? Am I going to compress it? Or am I going to do certain resiliency functions on the initiator and target to make sure that when I say I have written this data, it is guaranteed to have landed onto a disk or a set of disks in perpetuity. The back end is dealing with the either the network or a disk directly. So getting the handling the multipath across different paths in the network, being able to read and write a local disk, and running the different protocols. All of the protocols that we have inside of OPI and inside this demo today are the protocols found in SPDK. So we are not yet, I guess, innovating in this area. We're reusing the protocols that you can find in the SPDK project. And if we were to add another one, we would do so inside of SPDK. So in the demo, we're going to do a little Mystery Science Theater 3000 and play the demo. I'll do some voiceover, but we're going to create a device. We're going to set up remote targets. Oh, there it goes. Set up remote targets with multipath, so the data will go across different paths depending on the configuration through the API. We're going to set both bandwidth and IOPS limits on these devices. And then as a last step, we're going to encrypt the device as it goes across. So you can go and try to take a look at the data, and you'll see that the payload is entirely garbled and protected all the way from the DPU IPU into the disk and back. So
let's start with an overview diagram, which will accompany us for the rest of the presentation. On the diagram, you can see two physically separate systems. On the right,
I have it here, but not there. I wonder how I do that. Yeah, that must be it. It just went dark. Okay.
there is some storage target accessible over network. In our case, the storage target exposes two NVMe namespaces over TCP and has an IP address of 200.1.1.1. On the left, there is some host system, which could be a server with an XPU plugged in. The host runs client applications, and in the demo, we will start on it a simple FIO application. The actual local storage emulation software runs on the XPU to free up compute resources of the server CPU for all kinds of client workloads. It exposes a gRPC-based service with IP address of 200.1.1.3 on port 50051. This is the place where hardware and vendor-agnostic OPI commands are received. OPI Intel Bridge is the OPI software component which bridges these commands to Intel SDK. Please pay attention to the green boxes at the bottom of the diagram. These are no actual system components, but they indicate terminal panes, which will give us insights into particular components of the system and will be used to send gRPC commands to OPI Intel Bridge and for interaction with the host. This is the layout of the terminal panes that will be used from now on in the demo. Host pane.
This is great. We're all going to watch ads together now, I think. Oh, no. Skip ads. My kids are really good at that part. Here we go. Wow.
Pane is used for host interaction. Control plane pane is used to send OPI gRPC commands to OPI Intel Bridge. And the bridge pane shows the log messages on the bridge. Our first use case will be NVMe controller creation. We will use OPI gRPC commands to make two NVMe PCIe devices appear on the host. NVMe 0 will be a PF and NVMe 1 a VF. Let's see how this is achieved in practice.
Okay, in this video we'll observe how to create NVMe controllers by means of OPI API. As a first step, let's go to our host and see what we have there. Okay, we don't have any devices, and let's create our physical function first. For that purpose, we need to create our subsystem first, and then we need to create a physical function itself. So yes, controller is created, and then on host we need to find NVMe driver the physical function.
Great.
There we go. And what we have.
So now I have an NVMe 0 disk on my host.
Next.
Just from those creation functions over OPI.
Virtual function. First of all, we need to create a dedicated subsystem.
You'll see the command looks really similar.
Then we need to create the virtual function itself. Here you see
Bridge receives it on the gRPC server.
We need to go to host and find NVMe driver to that virtual function, right? And see what we have.
Now we have two controllers to create disks inside.
Virtual function.
The controllers we just created are not baked by any actual storage target yet. In this video, we will show how you can create a remote NVMe over TCP storage controller with multipath capabilities and connect it to our remote storage target using two different paths, one over port 4420 and the other one over port 4421.
Here we'll see how to connect to remote NVMe over TCP.
And we create different paths using different
OPI. So,
TCP ports, so that they'll take different paths in the network. They'll be hashed to different switches.
For each side, we have created controller with
potentially to different uplinks on the IPU.
So then we need to
for
create
network resiliency reasons.
For the controller here.
But this example here is showing how you would just call through OPI
to remote
APIs,
controller on this address,
connect the initiator and the target together.
Right. And let's create another path.
The target is running standard SPDK, so there's no
another port,
there's no requirement to have a DPU or an IPU on that target.
To the same target, but another port here.
And this demo is being run on the E2000s.
The first day that we signed up for Monday.com, our department was already able to connect our.
It makes it more exciting, really. It's like.
With the remote target connection, we can expose now two NVMe namespaces to the host. In this video, we will show how a device-level QoS limit can be set on the NVMe PF, which has the two namespaces attached. For the QoS, we can set both bandwidth and rate limits. In this video, we will set a common rate limit on the device.
So that if this host tried to push more than 5 kiloIOPS on that namespace, the hardware will slow down at those axes
what we've got
at the
VF, we've got our VF.
At the read and write level.
Also,
so nothing is dropped, nothing is lost.
Connected.
We just add more delay
some namespaces, and as a first step, we need to create namespaces for example, for VF, backed by those remote namespaces, right? So yeah, we issue creating namespace commands, and let's see what we've got.
The gRPC structure here about the volume.
We see those namespaces here. That's fine. As a next step, let's run FIO command against both namespaces.
So here's the
here
just going to run FIO to just put some dummy traffic on that
we are running
device.
Commands, right? Those are not performance numbers; they're just for reference. And we see like 85 kiloIOPS.
So he's running 85 kiloIOPS.
Namespaces.
That's not going to light anyone's hair on fire, but this is the performance demo.
To set QoS on device level, we need to set an OPI command. We need to update our NVMe controller.
So here's the command that he's doing, and there's the kiloIOPS equals 5 at the bottom.
reads for 5
We're just going to
kilohertz.
set that limit on the
There
device.
we go. And then we need to run our
Received by the
FIO
bridge, and
command
then
again on both
it initiates a rate limiter inside the IPU,
and we see
so that now on the host, we're at 5.003 kiloIOPS.
Yeah, that's fine. And let's see how
satisfying the SLA for that device, and also preserving
those limits to none.
IOPS for any other devices that will maybe share
update the controller
on that
command
same
with,
device.
no
Maybe
limits,
someone else's device,
and
someone else's disk
we run
that needs to use the resources. So we've isolated the resource utilization
and we see
using that command.
The numbers back like 80K, right? And let's remove our namespaces. We should commands to delete the first namespace and the second namespace. And see
now he's deleting the namespaces.
We've got like our TF and TF without any namespaces.
To run a different test.
In this use case, a rate limit will be set on a single namespace to showcase that a volume level QoS setting is possible with OPI API as well.
In this video, we'll see how QoS on volume level works. So we've got our PF, we've got our DF, we also have.
And now he's going to set a different rate limit for a volume.
Connected. So
again, another
let's
IOPS limit.
issue our OPI command to create QoS volume.
Kind of works in the same way.
To set
Same API.
the limit, max limit to 3 kiloIOPS on read write. For volume, needs to be
So he's applying the volume ID that he's created,
and
he's setting the read write IOPS to
2 namespaces.
3.
One is based on QoS volume.
That command gets received on the bridge, and now the bridge is going to go and apply that limit into the IPU.
To our host, we see our namespaces, and then let's run FIO, right? So let's run FIO against QoS volume. We run read write traffic and see what we've got. So we've got like 1.5K on read and the same numbers on write.
So he's showing that the total of read and write bandwidth set to 3
kilohertz, right?
In this case,
and
on the host.
We can run traffic against our namespace 2, right? And see what we've got there. And we see like 40K on read and 40K on write.
So this is a different volume. You can see that it's not limited.
And to wrap up, let's delete our namespaces and delete our QoS volume. And what we've got under our DF and VF without any namespaces.
To enable data at rest encryption, we will use OPI API to transfer crypto keys to the XPU and enable hardware-assisted symmetric crypto on the namespace connected to an NVMe VF. The plain text data, which reaches the locally exposed NVMe volume, leaves the host system encrypted for a secure over-network transfer to the storage target.
So this is like a self-encrypting disk. So I write
in this video,
regular
we'll
plain
see
data
how to
into
use
the virtual
volumes
disk.
in OPI.
It gets encrypted
First of all,
inside
let's
the
see
IPU.
what we've
And
got
then when it leaves the IPU to go over the network, it's entirely encrypted. When it lands on each of the different disks that it's being written to, that data will remain encrypted. And it will not be decrypted until it returns back to the IPU.
So first of all, let's send.
So he's going to show you how to call the function through the
there
API.
There we go. This encrypted volume is based
encrypt
on
the disk.
a remote namespace exposed from our target, right? And let's create a namespace for the encrypted volume. But this time, let's create a namespace for our virtual function.
You can see on our side here that we're using SPDK. And in the SPDK case, we're using the encryption function using
as a next
DPDK Quick Assist APIs. So as the data comes in, we use the AES encryption built into SPDK to encrypt the disks in hardware on the IPU.
What we've got.
And then
we got like all F.
Send it out. Right. So here is on the network the clear text. So you see
then let's
all F's is clear text.
Namespace.
He sent that over the network.
We should command to delete our namespace. We delete our encryption volume then. And as a next step, let's create namespace without encryption, right? You see what we've got on our volume, right?
So here, setting up the volume so that he can
let's see what we've got.
Encrypt data across.
And as you can see, you've got kind of garbage here, right?
So now when you look at the data as it's stored, it's all encrypted. Namespace. Doesn't look like all F's.
And again, let's create our encrypted volume, right? Encrypted volume.
You can see that when he went over the OPI API, he gave all the different keys needed to encrypt that device to OPI so that the infrastructure could encrypt it. And now he's decrypted it and showed you the clear text data from the perspective of the host. And so from the perspective of the host, didn't have to do anything to get that encryption to happen. But all of the data as it traversed through the infrastructure stored in the disks was all encrypted automatically.
As a next step, what if you create an encrypted volume with your own key? There we go.
So here you can see all the different details about how the parameters of how you want that encryption to happen, all the different keys.
Content. Again, we've got
and here again is the data that used to be all F's, now encrypted and garbled in different ways.
And as a final step, let's clean up and delete our namespace and encrypted volume. You see that we do not have any namespace here.
So he just deleted the encrypted volume. That's it. Back to the presentation. Maybe. Okay. So that was a demo, but it's a lot cooler when you are wanting to get something done and you can do it yourself.
Are you ready for retirement? Our free retirement planner shows you where you stand now and how you can meet your goals.
YouTube, you're like my comic relief here. That's amazing. I do want to retire. I think so. Yeah, I think so. What we want to do is we want to create a lab that, I don't know if I'm allowed to stand here, where folks can come in and have access to DPUs and IPUs that have been given by the vendors, and they can call these OPI APIs that and see the difference between the different implementations. So I call the OPI API like we just saw in the demo and be able to see this block storage virtualization in action. And once we're able to sort of build that baseline, then we can start building out more interesting use cases. Like a very common usage for DPUs and IPUs is to provide infrastructure for AI clusters. So in terms of being able to feed data into your cluster, into your model, using these block storage constructs that we just demonstrated can be really powerful. So when you have your cluster set up, you can move the disks in the right place so that that cluster can run its workload. Another common use case is to be able to do 5G, 6G parts of the wireless infrastructure. Being able to have data that follows wherever that installation has landed in the cloud or landed in the on premises. These DPUs and IPUs can provide that type of support, especially in the storage area. So, this lab is where we want to be able to demonstrate and experiment so that we can bring more users into this OPI community, so that we can make sure that we're actually solving that end user challenge that they have. So this lab is being set up right now, and we hope to have infrastructure to be able to get, authenticate people and get them into the lab and get them access to the systems very, very soon. So in summary, back to that original picture, we have these storage APIs running on a bunch of different systems. And I would say most of these systems can do all four of the steps that we demonstrated. You can manage the block devices on the host. They're all hardware isolated, can go to different tenants and go into different environments. We can have multiple paths across the network to get to the targets that we're trying to connect to. We can set limits to make sure that no one can get more or less IOPS than they're supposed to. And we can encrypt the data as it goes across. And we've talked about some of these other use cases like compression, more target work in terms of handling resiliency. We want to add these features over time, and we want to make these features available in the lab. So this is ongoing work that both Artyom and Philip are working on. They're active in this community. You'll see that this is open source development. So you go on the GitHub, you can see every single check-in, every new feature, every mistake, every bug that we fix. You'll see that in the GitHub, and it's an active project that has developers from different backgrounds, different vendors, trying to create this sort of common environment to set up use cases just like this. I'll open it up for questions. Yeah, go ahead. In this case, so the question was, how do you manage the keys? That's a really hard question. Has to do with trust. In this demo and in OPI, we are making the assumption, maybe, just to simplify our lives, that the infrastructure holds the key and has been given that key by the end user. So either the end user has a key and trusts the infrastructure well enough to provide that key, or the end user has asked the infrastructure to build its own key and to keep that key for themselves. Now, it all boils down to that core assumption that the keys are held by the infrastructure provider, your CSP or your cluster provider. So that is a fundamental question, and I think that there that's not a key management, and making that a little bit more secure and easier is not something that we have addressed yet at OPI, but certainly at Intel, we have a couple different, I would say, effective ways to move those keys around securely. But within OPI, we've just made that simplifying assumption that the keys are held by the infrastructure. Absolutely. Yep. Mm-hmm. But in real life, of course, you would need to have that key be securely distributed to the IPU, DPU, and then stored there safely. But one of the features of our IPU is that once you can program a key into the hardware, and then it can no longer be accessed. So once you go through that API and you program that key into our Intel device, there's no way that you can read a register, go and explore the memory space to find that key. So we have a secure key store on the device. I think that's pretty common across other hardwares, but you still have the challenge of getting that key from the user or something that was created on the user's behalf and putting it and getting it to the IPU. Other questions? Alrighty, it's been a good morning of lots of IPU and DPU and OPI talk, and I appreciate the time, and thank you.